Okay, so thank you very much. So today I'm going to be talking about nanotechnology, which you may have heard of before. Nanotechnology by herding molecules, hints from the theory. So my name is Daniel Packwood, and this is what I'm talking about. So technology, if you look in the dictionary, it's a process of making things. Okay, and humans have been making things in the same way for a very long amount of time. So we take some starting material, a very large amount of starting material, and we remove the parts we don't want until we obtain our target product. Okay, people have been doing this for many, many years. The manufacturing process has become more and more complicated, but this is the basic paradigm. Okay, we take something big and we make it small. People have been doing this for thousands of years, and it's become incredibly advanced. So here we have silicon, and from silicon we can make computer processors using the same process I described before. Now, computer processor is an incredibly sophisticated device. It contains over 8,000 million transistors, okay, according to some various sources. Transistors are very important. They control the currents inside of the processor. Now, how small is a transistor? Very small, 5,000 times smaller, thinner than a piece of hair. Okay? And this is a crazy thing. Society is wanting smaller and smaller products. So a computer from 10 years ago, maybe less than 10 years ago, can now be squeezed into your iPhone. Okay? And the iPhone 6, for example, is very thin, right? So there's a demand to make things thinner. Okay, people want things to be smaller and smaller. And how small can we go? There has to be some limit somewhere, right? So on the left-hand side here, we have a hair, a beautiful golden hair like my own. Okay, and on the right-hand side, we have a single molecule. This particular molecule is about 200,000 times thinner than a piece of hair. This is the smallest conceivable size that a material could become. Our computer transistor is about 5,000 times thinner than a piece of hair. That's where it is, a very long way from a molecule. This number here is very important, 20,000 times thinner. Okay, it's how far people think we can go with our current technology, how much smaller we can get than a piece of hair. There's various arguments around, there's various numbers. This is a ballpark number. Once you go beyond 20,000 times thinner, it's going to become very tough to make things smaller. Very, very, very tough. And therefore, if we want to go beyond that red line, which is still a very far away from the molecule, if we want to go beyond that line, we need an entirely new technology. Okay? Our current technology, as I've said before, is about making small things from big things. Today's talk's about nanotechnology. It's an entirely different concept. Nanotechnology is about making small things from really, really small things. What do I mean by that? By really, really small things, I mean molecules. Okay, nanotechnology is about making things from molecules. We want to take molecules and we want to build some kind of a structure with the molecules. Okay, this particular structure, if it was to exist, it would have a functionality like a wire. It could conduct electricity. Now, is this possible? We see with a molecule, you can't touch it. It's so small, you can't control it with your hands. So you've got to make things without using your hands. That doesn't sound quite right, does it? But actually, it's not a crazy idea. Let me show you a real-world analogy. Herding sheep. Okay, so on the left-hand side here, we have a whole lot of sheep dispersed over a paddock. On the right-hand side here, we've got some farmers, okay, very skillful people. They can herd the sheep. They can create a beautiful structure with the sheep, an ordered structure. Who's seen this, by the way, in real life? In Canada, do you see people herding sheep? You see cattle. Okay, probably a similar thing. In New Zealand, you see this all the time. So to me, this is a very comfortable concept. But the key point is they never touch the sheep. Okay, they don't touch the sheep, and the dogs don't touch the sheep either. They make a lot of noise, they wave their sticks. The dogs make a lot of noise, but they don't touch the sheep. Sheep are never hurt. So here's the topic of my research. This is literally the thing I study. What kind of stick, what kind of dog, okay, what kind of tools do we need to herd molecules? Okay, what kind of tools do we need to get the molecules to form some structure without using our hands? Okay, that is what I study. I'm trying to find these tools for making structures without using my hands. Now, I'm not a real scientist. I'm a theoretician. I'm more on the mathematics side of theory, by the way. Now, what's that mean, a theoretician? I don't do experiments. I don't go into the lab. The reason why I don't go into the lab is because I just can't do experiments very well. I stopped trying to do that many years ago. But I can do three things. I can do math. So I can take a concrete situation that we have in reality, I can simplify it, I can turn it into equations. And I can study the logic behind that abstraction. I can turn that mathematics into computer language, okay, programming. And I can feed that computer language into a big computer, and we can simulate the reality in the silicon. And we never go into the lab. The advantage of a theoretical approach is that it's very cheap and it's very quick. An experiment's very expensive, it takes a very long time. So I'll give you an example of one of my studies. We considered this molecule here, Br2Ba. Okay, why are we considering this molecule? I'll explain later. It's got a very special property. And the starting point for my study is, are there conditions where Br2Ba molecules will huddle by themselves? Huddling, this is what huddling is. It's where animals come together because it's cold. Okay, there's a whole lot of sheep huddling together in the cold. Are there conditions where the molecules will huddle together? For example, if we make the sheep cold, they'll come together. If we make the molecules cold, will they come together? We search for these conditions by computer simulation. And after a lot of work, we found the following. If you put this molecule on a copper surface, okay, the copper surface has the right chemistry. You put it on a copper surface, and you cool that surface down to minus 70 degrees Celsius. Okay, that's not that cold. It's cold, but it's not crazy cold. You can get the molecules to huddle. Okay, we get two kinds of islands, as they're called, patterns forming. One of them is an amorphous island. It looks like this here. That happens with about 30% probability, according to my theory. With about 70% probability, the molecules will assemble into this beautiful chain-type structure here. Okay? Now this chain looks like it could be useful for nanotechnology. Maybe it's got a conducting property. So the next question is, how do we boost the chain formation probability? Okay, we've found a way to create the chains, to create this amorphous island. How do we increase the probability of getting this chain structure? So we do more calculations. At the bottom, on the x-axis, we've got temperature. On the y, we've got the probability of forming chains and the amorphous island. As temperature increases, okay, the chain probability increases by a little bit, about 10%. What's happening is these amorphous islands are breaking apart into these chains. So this gives you a method of controlling the shape that is formed by molecules without touching them. Okay, you just increase the temperature a little bit. This is like forcing the sheep to go through a gate into a beautiful ordered structure like so. So this is one tool we can use for nanotechnology, a temperature control. No hands required. What about the dog? Okay, the farmer's got two tools. He's got a dog. What's our dog? Well, there's a thing that chemists can do. We can change the structure of a molecule. This is Br2Ba. Here we have Me2Ba. So we've only changed a tiny part of the molecule, just this little bit here. Very small change. Okay, that's what the dog does. It changes the molecule structure. And if you do that, you get a very high probability of forming the amorphous island, okay, under the same conditions. So this shows you that using the structure control, using the dog, we can force the sheep to go back through the other way. Okay, we can go from having a nice ordered structure to a disordered structure. Now, is this useful for nanotechnology? I don't know, but it's good to know what tools we've got and how they work. Okay, this shows you how you can change the shape formed by the molecules without touching them. Okay, this is all theory. None of this is real. It's all in my head, it's all on the computer. Now we've got to apply these tools for real. So we feed back to the experiment. So what I did, I had a talk with my experimental collaborators, Patrick Han and Taro Hitosugi, from Tohoku and Tokyo Institute of Technology. They did the same experiment, the same thing I did, but they did it for real. They put this molecule on the copper surface, and they observed the surface using a very powerful microscope called a scanning tunneling microscope. Okay, you can see individual molecules of this. That thing in the red circle is one molecule. This in the bottom circle here is a big amorphous island. It's made from many different molecules. So amorphous islands appeared, just like we see in our theory. And then they applied the temperature control. They increased the temperature just a little bit, and the amorphous islands became the chains, okay, like so here. So it's not just a theoretical concept. You can apply these tools in reality. That's a very important concept here. So they were able to apply this idea of forcing the sheep, forcing the molecules through a gate. They also changed the structure of the molecule. They tried to structure control. They tried to use a dog. And they were able to get the molecules to form an amorphous island. Okay, this is the picture at the bottom here. So they're able to apply the structural control and get the sheep to go back through the other way. They never touch the molecules. Okay, they change the structure. That's not touching the molecules, by the way. They change the structure, they change the temperature, they can control the shapes formed by the molecules. Okay, So before I showed you Br2BA, I said I use this for a particular reason. I said it's a very special molecule. What's special about it? Are these chains useful? Well, it turns out if you heat these chains up, they transform into a very special material called graphene nanoribbons. Okay, that's a picture of a graphene nanoribbon on the right there. At the bottom is a microscope image. It's a real image of a graphene nanoribbon. What's special about this? Firstly, it's much, much smaller than the transistor. Okay, 100,000 times smaller. And here's the cool part. Its conductivity is incredibly high, over 2,000 times higher than silicon. Remember, a computer transistor is made mostly of silicon. So this technology could be incredibly useful for making next-generation electronics. So the purpose of this slide is to show you that we can make real electrical materials using the nanotechnological approach without ever touching the molecules. Okay, but how are we going to get from this to a real device? This is the real question that's plaguing this field. We've first got to get these graphene nanoribbons, or whatever you make with nanotechnology, into real circuitry. Okay, we've got to replace the conducting lines with perhaps graphene nanoribbons. We've got to find tools for making more complicated structures. This is my role in the research, by the way. Okay, we need to have temperature control, we've got a structural control, but what's the third control? What control do we need to form this kind of bendy shape? Okay, we're trying to look for this in our theory. If we can find this, we can heat it up, we can turn it into a graphene nanoribbon. And then maybe we can integrate it into circuitry, like this little part down the bottom. And again, maybe we can find tools for forming this kind of island structure here. And we can integrate that into circuitry, and so on. And what if all circuitry could be replaced in this way? This is a big question. I expect at least a 20 times size reduction in the smallest of modern devices. At least. This is a scale picture, so your smartphone is going to become incredibly small. I don't know if this is useful or not, but it just shows you the potential that we have with this nanotechnological approach. But the big question that we have to address now is how do we control the shapes that are formed by molecules? That's what I'm studying, that's what my group will be studying, and we're going to try and solve this question. Okay, so thank you very much.